What's up, grade 9? How are you today? I hope you're fine, healthy, and safe. I am Teacher Bebs, and welcome to another lesson of Mathematics grade 9. Have you ever wondered how towers and buildings are constructed? How do you determine the distance traveled as well as the height of an airplane as it takes off? What about determining the height of the mountain? We can do all these things even if we are not in real place or situation. These are just some of many real-world applications of triangle trigonometry. Basic trigonometry deals largely with triangles. In this lesson, the solution of a right triangle will be the focus as a tool in solving real-life problems. Why are triangles used in bridges? Triangles are used in bridges because they evenly distribute weight without changing their proportions. When force is applied on a shape like a rectangle, it would flatten out. Before triangles are used in bridges, they are considered relatively weak. To solve that problem, engineers would put a post in the middle of a square and make it sturdier. This beam turns the square into two triangles that can each distribute weight evenly. The square is not able to buckle because the middle beam is fastened to the corners of the square. The corners cannot move any closer or any farther from each other because the beam keeps them in place. Architects use many triangles in bridges. Equilateral triangles are most commonly used in truss bridges, while scalene triangles are commonly used in more modern designs. Just about all bridges use right triangles. In your previous lesson, you took up the different parts of a right triangle. Let us try to recall them. Consider this figure. In a right triangle ACB, the side opposite the right angle C is the hypotenuse. The side opposite the two acute angles are the legs. The hypotenuse can be denoted by C. Similarly, the side opposite angle A can be denoted by A, and the side opposite angle B can be denoted by B. Side A is said to be adjacent to angle B, and side B is said to be adjacent to angle A. Using the sides of a right triangle, the definitions of trigonometric ratios of acute angle A are as follows. Sine A is equal to opposite side over hypotenuse, or A over C. Cosine A is equal to adjacent side over hypotenuse, or B over C. Tangent A is equal to opposite side over adjacent side, or A over B. Cosecant A is equal to hypotenuse over opposite side, or C over A. Secant A is equal to hypotenuse over adjacent side, or C over B, and cotangent A is equal to adjacent side over opposite side, or B over A. SOHCAHTOA is a mnemonic device used for remembering the equations. Notice that three new ratios at the right are the reciprocals of the ratios on the left. Applying algebra shows the connection between these two functions. Let us take a look at the following examples. Number 1. Find the values of the 6 trigonometric ratios of angle M in the given triangle. Let us have the solution. The opposite side of angle M is 21. The adjacent side is 20. And the hypotenuse is 29. Hence, using the 6 trigonometric ratios, we will obtain the following. Sine M is equal to 21 over 29. Cosine M is equal to 20 over 29. Tangent M is equal to 21 over 20. Let us have the reciprocals. Cosecant M is equal to 29 over 21. Secant M is equal to 29 over 20. And cotangent M is equal to 20 over 21. Let us have example number 2. In a right triangle, the legs measure 5 centimeters and 12 centimeters. Find the value of the 6 trigonometric ratios of the two acute angles of the right triangle. Let us have the solution. Let A and B be the acute angles and let C be the length of the hypotenuse. To find C, we use the Pythagorean theorem. Recall that the Pythagorean theorem states that the square of the hypotenuse is equal to the sum of the squares of the two legs of a right triangle, and it is denoted by the equation C squared equals A squared plus B squared. By substitution, we have C squared equals 5 squared plus 12 squared. Squaring 5 and 12 respectively, we have C squared equals 25 plus 144. Adding 25 plus 144, we get C squared equals 169. Finding the square root of 169, we get C equals 13. Remember, the length is never negative. Since the sides of the right triangle are now obtained, which are A equals 5, B equals 12, and C equals 13, we can now use the 6 trigonometric ratios for angle A. Sine A is equal to A over C, or 5 over 13. Its reciprocal, cosecant A, is equal to C over A, or 13 over 5. For cosine A, we have B over C, or 12 over 13. For its reciprocal secant A, we have C over B, or 13 over 12. Next, for tangent A, we have A over B, or 5 over 12. And for cotangent A, we have B over A, or 12 over 5. Also, using the 6 trigonometric ratios, we have the following for angle B. Sine B is equal to B over C, or 12 over 13. For cosecant B, we have C over B, or 13 over 12. For cosine B, we have A over C equals 5 over 13. And for its reciprocal, secant B is equal to C over A, or 13 over 5. For tangent B, we have B over A equals 12 over 5. And its reciprocal, cotangent B, is equal to A over B, or 5 over 12. Example number 3. A leg and a hypotenuse of a right triangle measure 2 centimeters and square root of 5 centimeters respectively. Find the 6 trigonometric ratios of angle A. Solution. First, compute for the length of the unknown leg and denote it as B. By the Pythagorean theorem, we have C squared equals A squared plus B squared. By substitution, we have the square of the square root of 5 centimeters equals A squared plus the square of 2 centimeters. Squaring the square root of 5 and 2 centimeters, we have 5 square centimeters equals A squared plus 4 square centimeters. Combining the similar terms, we have 5 square centimeters minus 4 square centimeters equals A squared. Therefore, a squared is equal to 1 square centimeter, or a is equal to 1 centimeter. Thus, sine a is equal to 2 over the square root of 5, or 2 the square root of 5 over 5, and its reciprocal cosecant a is equal to the square root of 5 over 2. Next, for cosine A, we have 1 over the square root of 5, or the square root of 5 over 5, and its reciprocal secant A is equal to the square root of 5 over 1, or the square root of 5. For tangent A, we have 2 over 1, or 2, and its reciprocal cotangent A is equal to 1/2. Before we end, let us summarize what we have learned today. In right triangle ACB, the side opposite the right angle C is the hypotenuse. The side opposite the two angles are the legs. The hypotenuse can be denoted by C, the corresponding lowercase of c. Similarly, the side opposite angle A can be denoted by A, and the side opposite angle B can be denoted by B. Side A is said to be adjacent to angle B, and side B is said to be adjacent to angle A. Using the sides of a right triangle, the definitions of trigonometric ratios of acute angle A are as follows. Sine A is equal to opposite side over hypotenuse, or A over C. Cosine A is equal to adjacent side over hypotenuse, or B over C. Tangent A is equal to opposite side over adjacent side, or A over B. For the reciprocals, we have cosecant A is equal to hypotenuse over opposite side, or C over A. Secant A is equal to hypotenuse over adjacent side, or C over B. And for cotangent A, we have adjacent side over opposite side, or B over A. For you to memorize immediately your trigonometric ratios, don't forget your mnemonic device, SO, KA, TOA. That's all for today, my dear learners. I hope you learned a lot from today's session. See you on our next episode. Enjoy learning mathematics. Don't forget to like, share, and subscribe to our Facebook page, Oplan Balik Eskwela, DepEd Luwag City, School Namin All In. Again, this is Teacher Bebs. Have a good day and keep safe, everyone.